with example with using the second Lyapunov method. And you hear me?
Yes.
Okay. And let's start and with whiteboard. Okay. And okay, let's prove that the origin is globally asymptotically stable for the next system. X1 dot equal to x1 cubed minus x1 x2 squared x2 dot equal to minus x2. Yeah, and okay, and when I calculate the eigenvalues of the matrix A of Jacobian, okay, let's calculate Jacobian first Lyapunov method. It's something in 0, 0 in origin. Okay, df x equal to 0, 0 equal to 0, 0, 0 minus 1, and lambda 1 equal to 0 and lambda 2 equal to minus 1. Here 0 and minus 1. Okay, we can say if this system is stable because this eigenvalue is 0, and we need to use the second Lyapunov method for testing the stability. Let's take positive definite function Vx, v from x equal to x1 squared half plus x2 half, and it's greater than 0 for all x1, x2 not equal to 0, and sorry. And the derivation v dot from x equal to x1 dot plus x2 dot, and it's equal to x1 minus x1 cubed minus x1 x2 squared and plus x2 and x2 dot minus x2, and it's equal to minus x1 in 4 degree minus x1 squared x2 squared plus minus x2 squared, and it's less than 0 for all x1 x2 not equal to 0, and then this system is global asymptotically stable. Any question? Okay, no question. The next example is from Khalil book. Example. Okay. This is page 86, and this 3, 1, 9, 19 and 1. you can check it in book. X1 dot equal to x2 and x2 dot equal to minus x1 cubed minus x2. Okay. Let's let's take the next Lyapunov function. Let's take the next Lyapunov function v from x. This classical 1/2 x1 squared plus x2 squared. Yeah, and then calculate the derivation is equal to x1 x1 dot plus x2 dot, and is equal to x1 x2 plus x2 minus x1 cubed minus x2. Okay, and it's equal to minus x1 x2 plus, sorry, here minus minus x2 squared and minus x1 cubed x2. Yeah, and what now? I think we can say anything because here is x1, x2 and this term, yeah. Okay, and we know that this term is negative if x not equal to 0, but the both another term we can say anything. Yeah. Okay, and let's try another Lyapunov function. For example, v from x equal to 1/2 x1 squared plus x2 squared and plus 1/2 x2 squared. Okay, sorry, what's this? But it's not classical. Here. Okay, and then v dot from x equal to x1 plus x2, x1 dot plus x2 dot plus x2 dot. It's equal to x1 plus x2 minus x1 cubed minus x2 and plus x2, and x2 dot is equal to minus x1 cubed minus x2, and it's equal to and it's equal to minus x1 on 4 degree minus 2x1 cubed x2 and minus x2 cubed. What we can say about the stability of the system now? It's a question. If anyone know.
Well, we cannot still decide the stability because we have the second term can be positive or negative.
Okay, thank you. Yes, we can decide because this first term and this second is negative, but this one, yeah, we can decide. But we can make assumption, yeah, and we can show that the middle term is smaller than the others, and that the derivative of the function v is non-positive, and we can use the fact that 2ab is less or equal to a squared plus b squared. Yeah, and I think you know this inequality. Yeah, and now we can say that we can take a is equal to x1 cubed and b equal to x2. Yeah, and then this term 2x1 cubed x2 is less or equal to x1 in 6th degree plus x2 in 2nd degree. Yeah, and what we have, v dot from x equal to this part, yeah, this minus x1 in 4th degree minus 2x1 cubed x2 minus in x2 squared, and this is less or equal to minus x1 in 4th degree, and this term is this one and or this one, and plus this term 2x1 cubed x2 here something like this x2 and minus minus x2 squared, and this is less or equal to minus x1 in 4th degree, and this term is plus x1 in 6th degree plus x2 in 2nd degree squared and minus x2 squared. Yeah, and okay, and now it's this is equal to minus x1 4th degree and 1 minus x1 squared. Yeah, and it's okay, and this is less than or equal to 0. Yeah, for x1 less or equal to 1. Yeah, and okay, what we can say now about the stability of the system? Anyone knows?
Wow.
Okay, now we proved that this system is local Lyapunov stable. Yeah, this is local Lyapunov stable. Yeah, because near the origin where dot x is less or equal to 0. Yeah, but we haven't x2 here. Yeah, and we can say only that it's local Lyapunov stable in the near the origin. Yeah, when x1 model of x1 absolute value of x1 less or equal to 1. Yeah, it comes from this part.
And what about x2?
Okay, we haven't x2 here. We haven't x2, and because we haven't x2, we can say only, we can prove only Lyapunov stability. Yeah, only stability. And we need to use Lassalle principle, something like this. Yeah, but we in this part of example we can't we use Lassalle principle in future. Yeah, on the in the yeah.
If we don't know, okay, now I'm a little bit confused. We know that if x1 is less than equal to 1, then it's Lyapunov stable. So
Yes.
the original function, the derivation of the original function vx should be less or equal to 0 for x1 less than equal to 1, right?
Yes.
So then it shouldn't matter what kind of x2 we use in that case. So
Yes. So it's no matter. Yeah, because x2 is equal to 0 here. We haven't x2 in this part. Yeah, and if we haven't x2, then we can say only that system is Lyapunov stable or only stable, and we need to use Lassalle principle, for example, and then we prove the asymptotical stability. Yeah.
Okay.
Let's try another Lyapunov function, the same equation, but another Lyapunov function. V from x equal to 1/2 x1 plus x2 squared plus x2 squared. Okay, and calculate the derivative of v. It's equal to x1 plus x2, and here's this x1 dot plus x2 dot. It's x2 minus x1 cubed minus x2 and plus 2x2, and this minus x1 cubed minus x2, and this is equal to minus x1 in 4th degree minus 3 x1 cubed x2 and minus 2x2 squared. Yeah, it's okay, and it's less or equal to minus x1 in 4th degree plus 3 x1 cubed and x2 minus 2x2 squared. Okay. Any question here in this step? Okay, and now it's the same like in previous step. Yeah, this step is the same. Now we have this middle term. This term negative. This one is negative, but we don't know if this term is negative or not. And we need, using the analogous estimate of the middle term, as in previous case, we get 3x1 cubed, and x2, this middle term, is less or equal to 3/2 x1 6 degree plus x2 2nd degree. Yeah, and with using this, we obtain that v dot x is equal to minus x1 in 4 degree and plus 3/2 x1 in 6 degree plus x2 in squared and minus 2x2 squared. And now, okay, and now this all less or equal to minus x1 in 4 degree 1 minus 3/2 x1 squared minus 1/2 x2 squared. Okay, so now we can see that this term is negative. Yeah, the first term is negative if and only if okay, v dot from x is less than 0 if x1 is less than square if x not equal to 0. Okay, and now we can say that the equilibrium 0, 0 of origin, or the origin is asymptotical stable. Yeah, but global is only local asymptotical stable. Yeah, this is local asymptotical stable. Yeah, because only near this x1 less than root of 2 divide 3. Yeah. Any question here? But global asymptotical stability is not guaranteed. Yeah. Okay, if you have any question, we can. Okay, now we make the next step. Okay, I show you how we can found the appropriate Lyapunov function, and then we come back to this example and try to find some Lyapunov function, and then maybe we can prove that this system is asymptotical stable. Yeah, global. Okay. The next example is x1. Okay, one. Okay, x1 dot equal to x2, x2 dot equal to minus x1 minus in x2 cubed. Okay, and what's now? Okay, sorry, okay, we solve this example maybe after another one, yeah, I'm sorry. Maybe some simpler example. This x1 dot equal to x1 cubed plus 2x2, and in x2 dot equal to minus x1 minus 3 x2 cubed. Okay, and now we need to find the Lyapunov function, some Lyapunov function that guarantee the symmetrical stability of the system, and we try to find this in the form v from x equal to f1 from x1 and plus f2 x2, yeah, and then the derivative of derivative of Lyapunov function is equal to df1 dx1 x1 dot and plus 2 d2 dx2 x2 dot. Yeah. Any question in this step? Okay. And now, okay, and now is equal to, in our case, this first derivation is minus d if 1 dx1 and this x1 cubed and plus df1 dx1, and here it's the second part, 2 x2, yeah, and this is this first, yeah, and the second one, and plus d, not plus but minus, sorry, because most terms with minus, and minus df2 dx2, x2 dot is x1, and minus df2 dx2 and 3x2 cubed. Any question here? Okay. Okay, now we can see from this that this part is depend on
one question.
Yeah.
Where does the minus come from in front of df1 over dx1?
Okay. I'm sorry. You're right. Here is minus. I'm sorry.
Okay, perfect. Thank you.
Okay. Thank you. Okay, this is minus. Yeah, and now we need to eliminate these two terms. for example, okay, this one is depend on only on x1, yeah. This part depend only on x2, yeah, but this one is depend on x2, sorry, and this is for x1 and so on. And we need to eliminate this part, yeah, this part. And what we can do is write df1 dx1 2x2 and minus df2 dx2 x1 is equal to 0, yeah. We want to eliminate this part, yeah. This is equal to 0. Okay, and then we only put, only rewrite that df1 dx1 2x2 equal to df2 dx2 x1, and then df1 dx1 divide to x1 and it's equal to df2 dx2 divide to 2x2, yeah. Divide to 2x2. Okay. Okay, what's now? This both, we can say that, okay, this both is equal to 1, is this one equal to 1, for example, yeah, it's the same constant, and then sorry, and then df1 dx1 x1 equal to 1, and from this df1 dx1 equal to x1, and the second part, this is df2, yeah, this df2 dx2 2x2 equal to 1, and then df2 dx2 equal to 2x2, yeah. And now we can integrate, yeah, this part and this one, yeah, and after integration f1 is equal to 1/2 x1 squared, and f2 equal to x2 squared. Any question here in this step? Okay, and now we know that this f1 and f2, and we can say, okay, v from x equal to f1 from x1 and plus f2 from x2, and it's equal to 1/2 x1 squared plus x2 squared. Okay, and what's now? Now we need to calculate derivation of v dot x equal to and equal to x1 dot plus 2x2 dot is equal to x1 and minus x1 cubed plus 2x2 and plus 2x2 and second minus x1 minus 3x2 cubed. Okay, and it's equal to minus x1 cubed in 4th degree plus 2x1 minus 2x1 and sorry and minus 6x2 in 4th degree. Yeah, this both terms eliminate. Yeah, it's equal to 0. Yeah, and now it's equal to minus x1 in 4th degree minus 6x2 in 4th degree, and it's less than 0 for all x1, x2 not equal to 0. Yeah. Any question? Okay, let's make one more example. Okay, and what we can say is that this system is global asymptotical stable. Yeah. Yeah. Okay. Okay, the next example is x1 dot equal to x2 and x2 dot equal to minus x1 minus x2 cubed, and the same. Let's find our v from x equal to f1 from x1 and plus f2 from x2, and then v dot from x equal to df1 dx1 x1 dot plus df2 dx2 x2 dot, and it's equal to the f1 dx1 x2 minus df1 df2 dx2 x1 and at minus x df2 dx2 x2 cubed. Okay, and what now we need to do? It's a question. Someone know?
Well, we need to find the f1 and f2 by integration, so we need to change the we need to find f1 x dx1 x1 is equal to df2 divided by dx2 times x2.
Okay, yes. Yes, we need to eliminate this part. Yeah.
Yeah.
Because here it's df2 dx2 x2. Yeah, it's okay, x2 cubed. But this part is depend this x2 and here x1 x2. Yeah, this x1 x2, and we need to eliminate this part. Okay, and now. Okay, thank you. And now I that this df1 dx1 x2 minus df2 dx2 x1 equal to 0. And okay, and df1 dx1 x2 equal to df2 dx2 x1, and the same df1 dx1 divide x1 is equal to df f2 dx2 divide x2. Okay, and the same df1 dx1 divide x1 equal to 1, and equal to 1, and df1 dx1 equal to x1, and after integration we receive that f1 equal to 1/2 x1 cubed, and the same we can do the same with df2 dx2 equal to x2, and f2 equal to 1/2 x1 x2 squared. Any question?
Yes, can we say that the equations are not equal to 1 but any other number and then get rid of the 1/2?
Yes, why not?
Okay.
Yeah, any constant. Okay, and now, but okay, any constant you can use. And now the final step, this v from x equal to f1 from x1 and plus f2 x2, and it's equal to 1/2 x1 squared, this part, yeah, and plus 1/2 x2, sorry, this part, yeah, and this part, x2 squared. And this is greater than 0, yeah, for all x1, x2 not equal to 0. And v dot from x equal to x1 dot plus x2 dot is equal to x1 and this x2 and minus x2 x1 and minus x2 in 4 degree. Yeah, and this is equal to minus x2 in 4 degree less than 0 for all x2 not equal to 0. Yeah, and what we can say about sorry. Okay, what we can say about the stability of the system now?
Well,
Okay,
it's stable.
Stable?
Asymptotically stable.
Why?
Because it's smaller or equal to 0 for any x1 and x2.
Not x1.
Oh, sorry. I meant.
Only x2.
Okay. Then from this we only know that it's stable, but we don't know if it's asymptotically stable because of the x1, and we need to find the stability from the principle. I forgot the name.
Pascal principle.
Yes.
Yes, you're right. This system is global stable. And now we can apply the Pascal principle. Yeah, okay. And as we know, x2 equal to we know that x2 equal to 0. Yeah, and if x2 equal to 0, then if x2 equal to 0, then okay, we can decide from minus x1, x2 equal to 0, x2 dot equal to 0, yeah, and we can decide from the x2 dot equal to minus from the second equation, x2 equal to minus x1 minus x2 cubed, and we can decide from this that x1 equal to 0, 2, yeah, and this system is global asymptotical stable. Okay, this gas. Any question? Okay, let's come back to our first example. Is this when we try three different Lyapunov function? I think 3 or only 2? Only 2. Yeah. No, when we try 3 Lyapunov function, and now we try to apply this method for searching the Lyapunov function. Yeah. Okay. This example is next. Only repeat the example here. This x1 dot equal to x1 equal to x2 and x2 dot equal to minus x1 cubed minus x2. Okay, and now we apply this algorithm. V from x equal to f1 from x1 plus f2 from x2, and v dot from x equal to df1 dx1 x1 dot plus df df2 dx2 x2 dot. Okay, and it's equal to df1 dx1, and here's this x1 dot, this x2, and minus df2 dx2 x1 cubed minus df2 dx2 x2. Okay. Okay, and what we need to do now? Someone know? Any idea?
We should eliminate the first two.
This one?
And the df2 dx2 times x1 cubed also.
Okay. Okay, thank you. We need to eliminate these two. This equal to 0. And okay, thank you. And now we do it. Okay, df1 dx1 x2 is equal to df2 divide dx2 times x1 cubed. Okay, and df1 dx1 divide x1 cubed is equal to df2 dx2 divide x2. Okay, and the same iteration, df1 divide dx1 divide x1, sorry, divide x1 cubed is equal to 1, and df1, therefore df1 dx1 equal to x1 cubed, and the second part is df2 dx2 divide x2 equal to 1 equal to 1 and df2 divide dx2 equal to x2. Okay. Okay, and now and Okay, and now we know that after integration, this f1 equal to x1 4 divide 4, and this f2 equal to x2 squared divide 2. Yeah, and now only put this f1 and f2 and our Lyapunov function candidate v from x equal to x1 in 4 degree divide 4 plus x2 squared divide 2. Okay, and okay, it's greater than 0 for all x1 and x2 not equal to 0, and v from x, v dot from x equal to 4 x1 cubed plus 2 divide 2 x2 and x1 dot x2 dot is equal to x1 cubed, and this first x2 and plus x2 and this minus x1 cubed minus x2, and it's equal to x1 cubed x2 minus x1 cubed x2 and minus x2 squared. Okay, this can go, and it's less than 0 for all x2 not equal to 0. Okay, and what we can say now about the stability of this system?
Also globally asymptotically stable?
No. Why asymptotically stable? Okay, here only this term, yeah? Minus x2 cubed by, we haven't this term x1, depend on x1, yeah? Okay, we can say that this system only global stable, yeah? Global Lyapunov stable, but global stable. And what we need to do now, if you want to prove the asymptotical stability of the system,
we need to use the lasso principle to
yes,
find dependency on x1, because that's not in the derivation. We only know that it's stable for x2.
okay, thank you. Okay, you're right. And okay, we say x2 equal, when if x2 equal to 0, then x2 dot equal to 0, and then the second x2 dot equal to minus x1 cubed and minus x2. Yeah, and we, if x2 equal to 0 and x2 dot equal to 0, then this x1 cubed equal to 0, 2. Yeah. And then x1 equal to 0. Yeah. And now we prove the global asymptotical stability of the system via the Lassalle principle and via this Lyapunov function, this special Lyapunov function. And now I can show you the MATLAB simulation, for example. Yeah. And okay, you see, I make this system x1 dot equal to x2 dot equal to minus x1 cubed minus x2, yeah, and x2 equal to minus 10, for example, yes, and x1, this initial condition equal to minus 20, yeah, and when I start the simulation, okay, and I hope that I show you this scope, yeah. Do you see this the scope, yeah?
Yes.
Yes, and you can see that when we start quite far from the origin, then our system is stabilized, yeah, and go to origin, and you can see that this system is asymptotically stable, yeah. And we can try some another initial condition, for example, this x1 not equal to minus 20 but only 20, for example, yeah, and something with plus, and then run, and I don't know if now the same. You see this scope, yeah?
Yes.
Yes, it's quite the same, yeah. The behavior is quite the same. We start with x1 equal to 20, yeah, and after a short time, yeah, it's go to 0. Yeah. Oh, okay. Okay, let's go to 0. Okay. So maybe here it's very close to 0, and it's select. Okay, and you can see from this example that we can try to choose different Lyapunov function. And for example, when we use this first Lyapunov function, this v from x equal to 1/2 x1 squared plus x2 squared, then we can say anything from the derivation of Lyapunov function, yeah, because we have these two bad terms, yeah, but then we try to use another Lyapunov function, and we prove that this system is local Lyapunov stable only if x1, the absolute value of x1 less or equal to 1. Okay, and then we prove with another Lyapunov function the asymptotical stability, but only
I'm sorry,
local.
but we don't see the whiteboard.
Okay, sorry. I show you. One moment. Okay, I try to start this whiteboard. I hope. Yeah, it's okay. Okay, and okay. I think here. This first example. Okay, this example. Yeah. Okay, we start with this Lyapunov function. Yeah. Now you see, yeah, this whiteboard.
Yes.
Okay, and we start with this Lyapunov function. This where from x equal to 1/2 x1 squared plus x2 squared. Then we can say anything from this this derivative of Lyapunov function from derivation, and then we try to check the stability with another Lyapunov function, this one, where from x equal to 1/2 x1 plus x2 cubed squared plus 1/2 times x2 squared. Yes, and then we calculate the derivation of our Lyapunov function candidate and Lyapunov function, sorry, and then we estimate with this kind of estimation that our system is local Lyapunov stable, yeah, for this x1 less or equal to 1, yeah, and then we try the another Lyapunov function, and we conclude that with using this Lyapunov function we can prove the local asymptotical stability, yeah, of our system, but only if x1, the absolute value of x1 less than root of 2 divided 3, yeah, this and then we try to find the appropriate Lyapunov function. You have this method. I think this one, this, yeah, okay, this is the last one, and then we try to find with this method our Lyapunov function, and with the next Lyapunov function, we from x equal to x1 in 4th degree divide 4 plus x2 squared divide 2, we prove the global asymptotical stability of the system, yeah, and we can you can see that it's very important to find the appropriate Lyapunov function, and this method is very useful, yeah, and so on. Okay, and now do you have any question? Okay, and now we calculate. We solve the another question, another system. Let's x1 dot equal to x2 plus a x1 cubed, so x2 dot equal to minus x1 plus a x2 cubed. Okay, and we can calculate the Jacobian f dx equal to this 3 ax1 squared 1 minus 1 3ax x2 squared, yeah, and in 0 0 it's equal to 0 1 minus 1 0, and the eigenvalue is equal to lambda 1 2 equal to plus minus e. Okay, and we can say anything about the stability with using the first Lyapunov method, and now we try to prove the stability via the second Lyapunov method. And let's take the positive definite function v from x equal to 1/2 x1 squared plus x2 squared, and is greater than 0 for all x1 x2 not equal to 0, and v dot from x equal to x1 dot plus x2 dot is equal to 2 okay equal to x1 x2 plus a x1 cubed and plus x2 minus x1 plus a x2 cubed is equal to x1 x2 plus a x1 in 4th degree plus minus x2 x1 and plus a x2 in 4th degree. This term eliminate, and this is equal to a x1 4 plus a x2 4 and it's equal to a x1 4 plus x2 4. Okay, and what we can say about the stability of the system if A R internet, maybe I have some problem.
No, I don't think so. The system is asymptotically stable for a smaller than 0, so for negative values of r, and the other side for any other number.
Okay, thank you. Yes. Now we can say that for A greater than 0, the system is unstable. Yeah, unstable. For A less than 0, the system is global asymptotical stable. Yeah, and for A equal to 0, someone know?
We cannot decide when A equal to 0 because
Why? We can decide.
well, because then the derivation is 0 everywhere.
And if derivation is 0 everywhere,
It's stable. Sorry, it's just stable. It's not asymptotic.
global or local? Global. Yeah.
Global stable.
Okay. Global stable. Yeah. Thank you. It's global stable. Yeah. Only stable. Or Lyapunov stable, for example. Yeah. Okay. And here, for example, we can say, for example, in this, yeah, this is interesting. When A greater than 0, then this system is unstable. Yeah, and it's because exists some definition of about the stability and about when system is stable and when system is unstable. For example, if we found or try some Lyapunov function here, yeah, when for all x1 and x2 not equal to 0, this v from x greater than 0, then, and when we calculate the derivation of v from x, and this derivation is greater for 0 for all, when it's greater from 0, when if we, if this v dot from x is greater for 0 for all x1 and x2 not equal to 0, then this system is global unstable or unstable, sorry. Yeah. And you can check if this system stable or unstable if when you calculate this v dot from x, and this v dot from x is greater than 0 for all x1 and x2 not equal to 0, then we can say that this system is unstable. Okay, and okay, maybe do you have some question about homework? This second homework?
I have a question regarding to the Khalil book. So we should rent it somewhere, I guess, and in the library it wasn't possible. So is it possible to get access to the PDF of the book? Or
okay, you haven't Khalil book, yes?
no.
Okay, it's a problem because I think in library only 10, maybe 10 or I don't know, maybe 15 books. And you can ask maybe someone to show you, or I don't know. You can ask Professor Chilikovsky, for example. I don't know what you can take the another Khalil book, not this nonlinear control, but for example, nonlinear system, the big one book. and many information or many materials you can find in this big Khalil book. Yeah.
Yeah.
Okay.
So it's called Nonlinear Systems, the big book where I can also find this.
Yes, Nonlinear System 3rd edition Khalil book. It's Khalil, the same. This I only write here no linear systems. Yeah. Because this first one, this nonlinear control, it's like a student book, but you can take this nonlinear system Khalil book and many examples and many. I think it's bigger, maybe twice than this nonlinear control book. But if you take this big book, I think it's okay. Yeah, you can find many information and
okay.
Yeah, from this big book. Okay.
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 Thank you.
I'm sorry. Thank you. And I'm sorry, I check you first homework this week and put you some comments. Yeah. And I think we can do maybe one more example. We have 5 minutes and okay. For example, X okay, x1 equal x1 dot equal to x1 x2 sorry x2 and x2. I have some trouble with internet, I think, because when I think we can finish. Yeah, and I show you. We can calculate some more examples on the next seminar. And if you have any question, you can write me a mail. Yeah, and please use email because when you write to Teams, I need some time to log in and so on. Yeah, and when you write your question via email, it's better for me. Yeah. Okay. Thank you. Bye bye. See you next week.